Thank you for joining us today for this interview session with a telecommunications network engineer candidate. This role is critical to maintaining seamless communication infrastructure and ensuring data transmission is secure and reliable. As the demand for robust network solutions continues to grow, so too does the need for skilled professionals who understand complex network architecture, can troubleshoot system issues efficiently, and stay ahead of evolving technologies. Today, we'll explore this candidate's depth of knowledge, hands-on experience, and approach to real-world networking challenges through a series of 10 in-depth questions. Let's begin. 1. Can you describe the core responsibilities of a telecommunications network engineer and how they impact a company's overall operations? A telecommunications network engineer is fundamentally responsible for designing, implementing, managing, and maintaining the data and voice communication systems within an organization. Their work ensures smooth internal and external communication channels, whether through landlines, VoIP systems, cellular connections, or satellite-based communication. In an increasingly interconnected world, businesses depend on reliable communication platforms for operations, customer support, and collaboration. Network engineers analyze current infrastructure, assess risks, and provide recommendations for scalability and resilience. They configure routers, switches, firewalls, and load balancers while also working with telephony systems and WAN/LAN environments. These engineers must ensure network security protocols are enforced and disaster recovery plans are in place. Their expertise often bridges IT and operational needs, ensuring bandwidth meets business demands. With remote and hybrid working becoming standard, network engineers also support VPNs and secure remote access tools. Their contributions affect operational efficiency, downtime, customer satisfaction, and even company reputation. By staying proactive, monitoring traffic, and swiftly resolving issues, they keep communication flowing. 2. What are the key networking protocols that a telecommunications engineer must be proficient in, and why are they important? Telecommunications network engineers must be fluent in a range of protocols that govern how data is transmitted, received, and routed across various networks. Among the most essential protocols is the Transmission Control Protocol/Internet Protocol, TCP/IP, which is the foundation of modern network communications. Engineers also need to understand User Datagram Protocol, UDP, especially when dealing with real-time data transmission like video conferencing or VoIP. Routing protocols such as OSPF, Open Shortest Path First, BGP, Border Gateway Protocol, and EIGRP, Enhanced Interior Gateway Routing Protocol, are vital for determining optimal data paths and ensuring network efficiency. For secure communications, protocols like IPsec, SSL/TLS, and HTTPS come into play, especially in enterprise environments where data integrity and confidentiality are non-negotiable. SNMP, Simple Network Management Protocol, helps in monitoring and managing network devices, allowing engineers to track performance, detect anomalies, and perform maintenance tasks proactively. Engineers working with wireless systems should also know Wi-Fi standards such as IEEE 800 and 2.11. In telephony, knowledge of SIP, Session Initiation Protocol, is crucial for handling VoIP communication sessions. These protocols allow devices to interact, data to be correctly routed, and security to be enforced. Understanding how they function individually and together gives engineers the toolkit to design reliable, scalable, and secure network architectures. 3. How do you approach designing a scalable and secure network infrastructure for a large organization? Designing a scalable and secure network infrastructure involves a comprehensive assessment of current and projected business needs, security risks, and future growth. First, an engineer must gather detailed requirements including user load, type of applications, bandwidth expectations, and geographic distribution. The next step is developing a layered architecture, often using the core, distribution, and access model, which helps manage traffic efficiently while allowing for expansion. Engineers must select hardware like routers, switches, and firewalls with modular capabilities to accommodate future upgrades. Redundancy is key, therefore, high availability configurations, load balancing, and failover systems are built in to avoid single points of failure. For security, the design integrates firewalls, access control lists, segmentation through VLANs, and intrusion detection prevention systems. Encryption standards like VPN for remote access and end-to-end encryption for sensitive data ensure confidentiality. Scalability also involves cloud integration, where hybrid architectures offer flexibility. Automation tools like configuration management systems enable efficient updates. Engineers also incorporate network monitoring tools for visibility and rapid troubleshooting. 4. Can you explain your process for troubleshooting network performance issues in a telecommunications environment? Effective troubleshooting begins with identifying the scope of the issue. Is it localized, affecting a group, or system-wide? A structured approach starts by gathering user reports and verifying symptoms. Next, engineers use tools like ping, traceroute, and packet analyzers Wireshark to diagnose connectivity or latency problems. Monitoring systems such as SolarWinds or Nagios provide historical performance data that can reveal trends or irregularities. If performance degradation is observed, the next step is to isolate layers, checking physical connections, cables, ports, configuration issues, VLANs, routing tables, and resource usage, CPU memory on network devices. Engineers check whether congestion is due to bandwidth saturation, misconfigured QoS, or faulty equipment. DNS misresolution or DHCP lease exhaustion are also common culprits. Once isolated, temporary workarounds may be implemented while permanent solutions are deployed, like rerouting traffic, replacing cables, or updating firmware. Documenting the incident, response steps, and resolution is essential for future reference. Root cause analysis follows, ensuring the same issue doesn't recur. Where applicable, lessons learned may lead to process improvement, like revising monitoring thresholds or enhancing alerting systems. This process relies on deep protocol knowledge, familiarity with the organization's topology, and a calm, methodical mindset. In multi-vendor environments, coordination with support teams may be necessary. 5. What role does network security play in telecommunications engineering, and what measures do you implement to ensure it? In this field, where vast amounts of sensitive data traverse internal and external networks, any vulnerability can be exploited, leading to breaches, service disruptions, or legal consequences. Engineers play a critical role in preventing unauthorized access, data leakage, and denial of service attacks. One of the first layers of defense is physical security, ensuring restricted access to hardware. Logical defenses include firewalls, access control lists, and intrusion detection prevention systems. Engineers configure these to inspect inbound and outbound traffic, filtering malicious content. Encryption protocols such as IPsec, SSL/TLS, and VPNs are used to protect data in transit. Network segmentation through VLANs and zero-trust architectures further isolates sensitive data zones. Engineers also implement authentication measures, ADIUS, TACACS+, or two-factor authentication, to regulate user access. Regular patching and firmware updates prevent known vulnerabilities from being exploited. Monitoring tools provide real-time alerts for anomalies, while logs help identify breaches post-incident. Security also involves compliance. Engineers must understand and enforce standards like ISO 27001, NIST, and industry-specific regulations. 6. Describe your experience working with VoIP systems and how you ensure their optimal performance. Voice over Internet Protocol (VoIP) systems have revolutionized modern communications by enabling voice calls through IP networks. My experience includes deploying and maintaining enterprise VoIP solutions, such as Cisco Unified Communications Manager and Asterisk. Setting up VoIP involves configuring SIP trunks, PBXS, and softphones while ensuring that firewalls and NATs are properly set to allow media traversal. Ensuring optimal performance begins with network readiness. VoIP requires low latency, minimal jitter, and low packet loss. I conduct pre-deployment assessments using tools that simulate call loads and monitor network performance. Quality of service, QoS, is configured to prioritize voice traffic over less time-sensitive data. I monitor MOS, mean opinion score, and implement jitter buffers to improve call clarity. Bandwidth planning is essential. I ensure sufficient headroom for peak usage and redundant pathways. In terms of troubleshooting, I use tools like call detail records, CDRS, packet capture tools, and SIP debuggers to resolve issues like dropped calls or poor voice quality. Security is also crucial. I implement TLS and SRTP to encrypt signaling and media streams, and firewall rules to block unauthorized VoIP traffic. 7. How do you stay updated with emerging technologies and trends in telecommunications networking? The telecommunications industry is evolving rapidly, driven by advancements like 5G, SD-WAN, cloud-native infrastructure, and AI-based network management. To remain effective and relevant, a telecommunications network engineer must continuously upgrade their knowledge and skills. My approach begins with regularly reading industry-leading publications such as IEEE Communications Magazine, Network World, and Telecoms.com. I subscribe to vendor-specific updates from Cisco, Juniper, and Fortinet, which often share white papers, product releases, and technical webinars. Attending industry conferences and events, such as Cisco Live, Mobile World Congress, or Black Hat, exposes me to emerging technologies and offers hands-on experience with new tools. I also participate in online communities and forums like Reddit's networking subreddit, Stack Exchange, and network engineering Slack groups to exchange knowledge and troubleshoot with peers. Certifications are another pillar. I pursue credentials such as CCNP, CompTIA Network, and VMware NSX, which help structure my learning around real-world application. I follow influential voices on LinkedIn and Twitter who discuss trends in SDN, edge computing, and automation. Additionally, I experiment with lab environments, using virtual machines and open-source tools like GNS3 or EVENG to simulate scenarios and gain first-hand experience. 8. What experience do you have with cloud-based networking solutions like SD-WAN, and how do they benefit organizations? Software-defined wide area networking, SDWAN, is transforming how organizations manage connectivity across distributed locations, especially in hybrid or cloud-first environments. I have deployed and managed SDWAN solutions from vendors like Cisco Viptela and Fortinet, assisting clients in replacing traditional MPLS links with more agile, cost-effective broadband or LTE connections. My experience includes defining application-aware routing policies, managing centralized controllers, and setting up automated failover protocols. SDWAN allows granular visibility into network traffic, enabling IT teams to prioritize critical applications like video conferencing while throttling non-essential usage. One significant benefit I've observed is cost savings. By reducing dependency on expensive MPLS circuits and leveraging local internet breakouts, businesses save substantially while improving speed and reliability. SDWAN's central management portal simplifies policy enforcement across sites, improving security and response times. Built-in encryption and firewall capabilities also reduce the need for additional hardware. I've also integrated SDWAN into multi-cloud environments where traffic routes dynamically between AWS, Azure, and on-prem data centers, enhancing resilience and performance. 9. How do you ensure high availability and redundancy in network infrastructure for mission-critical applications? Ensuring high availability and redundancy is paramount for supporting mission-critical operations that can't tolerate downtime, such as healthcare systems, financial platforms, or emergency services. My approach begins with designing fault-tolerant network topologies, such as dual-core switches, redundant aggregation layers, and multiple access points. Redundant power supplies, dual uplinks, and hot-swappable components are standard in my infrastructure choices. I implement link aggregation and load balancing to evenly distribute traffic and provide failover in case of port or link failure. Protocols such as HSRP, Hot Standby Router Protocol, VRP, Virtual Router Redundancy Protocol, and Spanning Tree are configured to ensure router and switch redundancy. For WAN connections, I set up multipath links, such as MPLS and broadband, to provide automatic rerouting if one fails. I also work closely with data center teams to ensure server clusters are designed with HA features, using virtualization tools like VMware HA and Hyper-V failover clustering. Real-time monitoring via platforms like PRTG or SolarWinds alerts us instantly of anomalies. I schedule periodic failover tests to validate configurations. 10. Can you discuss a challenging project you handled as a telecommunications network engineer and how you resolved it? One of the most challenging projects I led involved migrating a global enterprise from a traditional MPLS network to a full SDWAN solution across 50 branch offices. The complexity stemmed from minimal documentation, legacy equipment, and strict uptime requirements due to financial operations in different time zones. My first step was conducting a thorough audit of the existing network and identifying dependencies that could affect migration. I developed a phased rollout plan that included site prioritization, stakeholder coordination, and vendor support timelines. Each site was assessed for readiness, including circuit provisioning, hardware procurement, and compatibility testing. The challenge intensified when we encountered routing conflicts between legacy VoIP systems and the new SDWAN appliances. I resolved this by segmenting the voice traffic via VLANs and applying QoS policies that maintained call quality during peak loads. I used simulation labs to mirror configurations before deployment, reducing the chances of error. During migration nights, we had a dedicated war room with real-time monitoring dashboards and escalation paths. We completed the project ahead of schedule with zero downtime incidents. A telecommunications network engineer must combine technical expertise, adaptability, and strategic thinking to build secure, high-performing, and future-ready networks. Through proactive planning, continuous learning, and resilient design, they ensure seamless connectivity that drives modern digital transformation and organizational success.